This should be obvious, but let's just so we're all on the same page. Tell us the difference between pure and applied math.
Pure math is curiosity-driven math. We see patterns in very abstract things like numbers or shapes, and we just ask, does this pattern keep continuing? It's not necessarily motivated by any practical application, or maybe it started out that way, but people just kept asking questions.
Would that include people who are obsessed with what's going on in the sequence of digits of pi?
In principle, yes, that is part of pure mathematics. It turns out not to lead very far because there basically aren't any interesting patterns there.
Wait, but did you prove that there are no interesting patterns?
This is actually still an open question.
So it could be that the fact that there's not an interesting pattern is itself an interesting fact.
Right, except that we know that like 99% of all the numbers in the world have no interesting patterns. And it's actually only a very small fraction of numbers that actually have something detectable going on. So the fact that pi is part of the 99% is, in retrospect, not exceptionally interesting.
Do we have a theory why 99% don't have a pattern?
It comes from a law of probability called the law of large numbers. Like if you pick a number randomly, just for every digit you roll a die, a 10-sided die, and you select digits at random. The law of large numbers says that 99% or 99.99% of the time, you never see any patterns. You get as many zeros as ones, as many ones as twos. There's only a very small fraction of numbers that exhibit bias. It's a very useful law. This is why, for example, we can do statistics polling. Like if you want to poll 300 million Americans and see what they're thinking, you can't poll 300 million Americans, but you can poll 1,000, 2,000. And the law of large numbers actually tells you that as long as you poll a very representative set of people, the outcome of that poll is actually pretty close 99% of the time to the general population.
So I could ask a question that you might be able to answer. How many digits of pi would I have to roll out before I got 10 nines in a row?
That would be about 10 to the 10. So I guess 10 billion.
Okay. All right. We got an answer for that.
You're both wrong. It's 11 billion. I'm the guy that knows nothing and you're both wrong. Why are we doing it now?
Okay. So now applied math, the world, other than mathematicians, care about the answer in applied math.
Right. Yeah. So applied math, it's still not quite directly applying to the real world. That's what scientists and engineers do. But it's about the mathematics that is of practical value to those scientists. So an atmospheric scientist might care about predicting climate or the weather, and applied mathematicians might develop the software or the equations to actually model the atmosphere or oceans. They may not actually work directly with real data. They may only work with sort of test data or something, and it still has a lot of theory to it. But it's sort of intermediate between the pure mathematicians and scientists and engineers.
We face that a lot in astrophysics, where you can generate data that you can then apply your ideas to see if that works, and then you check later to see if the data you generate matches what you actually end up observing. So just the methods, tools, and tactics.
So when does applied mathematics sort of do a cheat, if you will, right? Sort of simplify things intentionally, drawing on pure mathematics. And where's that line where it's too much of a cheat or it's just enough of a cheat that it's still... Do
you mean approximation?
Yeah, well, the term is intentional simplified reality, right?
Yeah. So there's a spectrum. So the real world is messy, and if you try to incorporate every single aspect of it, it's just too much to model, and you can't see the forest for the trees. So mathematicians intentionally simplify reality. They work with what's called toy models. Physicists call them spherical cow type assumptions, where you want to model a cow. It's actually easier for the physics if the cow is a complete sphere and frictionless. That's not realistic, but it's a good starting point. And then over time, you decide to add some friction, add some legs to the cow. But you start with the easiest cases to get some an initial idea. I guess the difference between math and the other science and basically anything else is that we can change all our hypotheses and work with these toy cases. Like, if you want to build a bridge and you're an engineer, you can't just build a toy bridge over a creek first and then build your way up to a real bridge. If you're a heart surgeon, you can't do some experimental surgery on rats or something first. And then, well, I guess in training, maybe you do. But
mine has. That's why I have a bad ticker.
Okay, well, my condolences. But in most professions, you don't get to play your toy models because you're not allowed to fail. But in math failure is very, very cheap. You try a problem, you don't solve it, fine. You just toss the paper away and you try again. No one gets hurt, no one dies.
Yeah, the patient doesn't die. Yeah,
exactly.
Yeah, and let me add something because you just blew by the spherical cow. It's worthy of another comment. Okay, so in physics, everything is about simplification because often the details, while they may be interesting, don't actually influence the outcome in any important way. Okay, and if they do, you would have solved the case then to see how it influences the outcome. So here's the point. You're tasked with, I want to design a cow that can maximize milk production, okay? So then you say, consider a spherical cow, okay? So a sphere holds the maximum amount of milk for the area, okay? The surface area.
Okay, where are the legs and where's the head?
So now, if you add legs and a head and a tail, and okay, that reduces the number, but it means I have calculated the upper limit to how much milk the cow is going to make.
Because what is that sphere?
The sphere, exactly. So you can't come in later and say, here, have the cow produce 5 times as much.
Having those details of legs, tail, and head.
It subtracts from the total. Yes.
That's the detail that you said doesn't matter. Matters.
No. Well, what I'm saying is it caps how much you can think about that problem. It keeps everybody in the same room.
Got it.
Yeah. It's not an unlimited place to guess outcomes.
Have you found that applied mathematics can change a settled pure math theory? Has that ever gone back and sort of...
Well, let's lead into that by asking, tell us about unsolved problems in mathematics. And when they're solved, who solves them? Is it the computer person? Is it the pure math person? Is it something else?
Is it Matt Damon writing on a board when he's a janitor?
Exactly.
Come on.
Well, increasingly, there's a conversation going in all directions. So traditionally, pure mathematicians just experiment with patterns, and they based on analogies and intuition they build up, they propose that some phenomena that they see for one type of pattern also extends to some other setting. But sometimes it comes from the physical world. Physicists notice that something keeps happening. So, for example, there are these laws in physics that seem to be universal. That there are certain distributions, like the Bell curve distribution is an example of a universal distribution. If you plot, say, the heights of people or the size of cows, if you wish.
Can I just tell you something right now? I want a milkshake in the worst way. I am so craving one. Anyway.
But lots of distributions in nature have the same shape. In this case, a bell curve. There's even a meme about it on the internet.
And we would, in physics, and I think in pure math, it's a Gaussian curve.
Yes, that's the name for it. Yes.
Named after Gauss, brilliant mathematician, one of the most brilliant there ever was, I think.
Yeah, so mathematicians did actually find an explanation for why this curve appears all the time. It's something called the central limit theorem in probability. But there are some other distributions that physicists have discovered that we haven't yet fully explained why they show up so often, like gaps between spectral lines, and it's more technical to explain. But yeah, there are laws that physicists and other scientists have found are universal, and mathematicians and they're a good source of conjectures for mathematicians to work out. Yeah, well, mathematicians are in some ways exploring other universes, but just very abstract numerical universes, not as interesting as the sci-fi alternate universes.
So I mean, to put this in sort of practical terms, pure math versus applied, it's like you're painting a room, and you exactly calculate the number of gallons of paint. And then 2 days later, you've made 3 trips to Home Depot because you need 3 more gallons, and you're going to have a nervous breakdown because you didn't. That's the applied part, right? Once you get into it, you sort of go, oh, wait a minute, I didn't factor this in. And that's sort of what happens with applied math. And it would then correct some of your pure math calculations, right? So it's sort of this symbiotic relationship between the two. Right. Yeah.
So Vladimir Arnold, who is a famous mathematician, he once wrote that mathematics is the part of science where experiments are cheap.
Oh, I like that.
before you invest billions of dollars in a new telescope or a collider or something, you do the math and you see what is theoretically possible, maybe assuming spherical cows and things. But it tells you in theory what you can and what can't do, and it sets good targets, and then it allows you to allocate the more expensive resources more intelligently.